Okay, so last time we started the triangles. Three vertices. And three edges, then three angles. So we have three interior angles, A, B, C. Another way to draw this, we use three lines. This will be the three interior angles and three exterior angles. And we showed that the summation of the three interior angles the summation of the three exterior angles. Let's label this X, Y, Z. Another implication that's very easy to see is that each exterior angle A, B, C at angle A, at exterior angle X, for angle A you have two remaining interior angles, B and C. Similarly, angle Y, C. Each exterior angle is the sum of the opposite two interior angles. How do we prove this? Amy, what would you do? Why this angle equals to the sum of B and C? Do we use this angle? So what's the sum of angle A with X?
180.
And what's the sum of A with B and C?
180.
Now, if we subtract A from this, what can we say about these two angles with this one?
Those two added together would be the supplement of X.
Yes. So the proof is a direct proof because we know that X angle A is 180, X angle A from there we conclude X a direct proof, a very useful property. Then we introduce the congruence of two triangles. So here we should be careful. The order matters here. If we change the order, they give us different relation. Okay, they are different. To determine when two triangles are congruent, there are 6 conditions, but the side angle side theorem tells us we only need 3 of them. If we draw a graph, keep giving me this isosceles triangles. We can pick a pair of angles. If we pick angle B and angle F, this will be the angle condition. And the two sides, they must be the two pairs of adjacent sides to B. AB and EF, same lines. BC and FG, same lines. So this is the side-angle-side theorem. This SAS. At the end of last class, we introduced the isosceles triangle. It's a triangle with 2 equal angles and 2 equal sides. These 2 angles B and C have the same measure. And A and B, the 2 sides. Okay. So because of this, we call these 2 sides. It's not an angle, that's AC. These two sides are the two legs. Then BC equals the base. Okay, so this is the definition of a triangle being isosceles. Two angles, same measure. Two sides, same length. Then the following proposition. If the two sides of a triangle have the same length, consider then we can derive the second condition. Okay, so that means in the definition of the isosceles triangles, we have two of them, but we can only check this one because this condition can be derived from the next one. Okay. Okay, let's think about it. How do we prove this? Why the two angles must be the same? Aaron, what do you think? How do we check this? Why the two angles must be the same?
Well, because that last line is a base, right?
Uh-huh.
And since there's AB and AC, and that's a base, then therefore there's two angles consisting of the base that are equal.
Okay, so in the end, after we verify this, the two conditions, they imply the triangle is an isosceles triangle. At this moment, we haven't established that yet.
Oh,
We cannot use this yet. We want to prove this. If we have both, then we see this triangle is an isosceles triangle. Okay, so to prove this, we consider a pair of triangles, and we will show that they are congruent. Okay, let's see. What? Aren't they the same triangle? What's the difference between them? Jessica, what is the difference between them?
I don't think there's any like difference.
So the order are different. This one B, C, this one C, B. So the orders are different. Therefore, even though they share the same collection of vertices, one A, B, C, but the other A, C, B, one A, the other one Okay, so these two, we treat them as two different triangles. We want to check, are they congruent to each other? Now the only theorem we learned is the side-angle-side theorem. We want to check if we can apply the side-angle-side theorem. What is unknown is whether these two angles are the same. That's what we wanted to check. What's known is these two triangles, they share the same angle A. So the first observation, angle BAC, angle CAB. So because it's the same angle, even though the orders are different. Now, one pair of this angle for triangle ABC will be AB. Now, A to A, B to C, the corresponding side will be AC. And we know they have the same length. It's our condition. Then the other side of the angle will be AC. AC, this is the first third. Let's check the first and the third vertices of the second triangle with AB. Okay, so a pair of triangles, ABC, ACB, this have a pair of angles, same measure, and the adjacent sides, same length. So we can apply the SAS theorem. Okay, the two triangles, they are congruent. The corresponding angles are the same. The corresponding angles, first to first, second to second, third to third. In particular, this pair give us what we need. Okay. So an application of the side-angle-side theorem tells us if the two sides have the same length, then two angles must be the same measure. Okay. Then we will use this to prove another theorem. So this one we call it side-side-side. Use SSS for short. Okay, we consider a pair of triangles. Now, if we have three pairs of the sides, AB with EF, first pair, ACEG, second pair BCFG. If each pair of angles have the same length, so this means and. Okay. Under these three conditions, we conclude the two triangles are congruent. Okay, let's think about it and how we're going to prove it. We have two triangles, three pairs of their sides, each pair have the same length. Then we claim they are actually congruent. The angles must be the same. Okay, let's try. Okay, so we will place the two triangles next to each other. So because these two sides have the same length, and we put them next to each other. So initially it's this. Okay. To prove they are congruent, I'm going to make a copy of this triangle under this with B constant with F, C with G. Because they have the same length, this make the copy possible. This will be the copied E. I copied F, copied G. Okay, so I make a copy of this triangle. So it's maybe a reflection, then a shift. In particular, these two triangles, they are congruent. Next, we want to check these two triangles, they're congruent. We start with the two angles. How to justify this? Okay, to justify it, I'm going to connect A and E. Okay, now let's consider the two triangles. Angle A, B, E. Because AB and BE, so this is the B is same as F, this is same as BF, they have the same length. So this triangle, ABE, we have two equal lengths. We can apply the previous theorem. If we have a pair of edges with the same length, the two angles are the same. So by the previous theorem, these two angles are the same. Angle BAE, angle BEA. This pair must have same measures. Similarly, we consider the other one, ACE. We want to conclude that these two angles are also the same. We wanted to say CAE, CEA. Why? How could we do this? Kira, an idea why these two angles must be the same?
Which one exactly is CAE?
So
Or is it the sum of all?
CAE to be this angle. So the middle point is the turning point. C to A to E to be this angle.
Okay.
Uh-huh.
So CA is you would go to E first, so that would be basically like a reflection to the A because like A, B, and B, E are equal, I guess.
So A, B, and B, E, they are equal. This is our condition because B and F overlap. The same way, AC and EC need to be this condition. AC and EC, G and C overlap. So AC equals. Because E is the same as G, C is the same as G. EF, here what I meant is not a B, but okay. So the two, for this triangle, the two sides same length. That means that this is an isosceles triangle. So the two angles must be the same. So we applied the previous theorem. Equal sides, equal angles. We applied it twice. We applied it once, this triangle, twice, second time to this triangle. 1, 2. Then we conclude the two angles are the same measures. In particular, angle A is the summation of the two angles. BAE, BEA, same measures. CAE, CEA same measures. Now, the summation of these two angles give us angle E. Okay, so we verified one pair of the angle are the same. Then we can combine with the two conditions. ABEF, AC, and EG. ABEF, AEAC. We have the side-angle-side theorem. This implies the two triangles are congruent. Okay. This is the side-side-side theorem. If a pair of triangles with three pairs of edges with same length, then they must be congruent. In the proof, we use the previous properties of isosceles triangles, and we applied the side-angle-side theorem. Okay, any question about this proof? Aaron, what do you think?
So you're saying that SSS and SAS are sort of related? Is that one of the points?
So we used this theorem SAS to derive the side-side-side.
Oh,
Uh-huh.
so basically still related, yes, I see.
It's possible that there are different proofs without using this SAS. So our proof use it, maybe there are different proofs. And then later you will see a mathematical theorem may have a lot of different proofs. Okay. Now we have this side-angle-side. We move to the next one. Called
ASA?
yes, angle side angle ASA theorem. Again, we consider the two triangles. Now, the assumption we have is assume AB and the EF same length, and the two neighboring angles so AE BF angle side angle. Then we conclude
Is ABC congruent to EFG this way?
ABC must be congruent EFG. Okay, let's see how can we prove this theorem? Why? I'm going to draw a pair of triangles. Then we figure out how to prove it. To keep correcting me, I don't want to be. We have equal side angle. Then we claim the two triangles are congruent. How can we prove it? Okay, let me check. Yeah, sure. Okay. Okay, so what I'm going to do is I'm going to translate, maybe shift. I'm going to shift this side to AB so that E overlaps with A and F overlaps with B. Then these two lines, AC and the shifted line, EG, they will overlap. So shift. AC and EG. Because the two angles are the same. So from the same line, then the same angle, we have one line. In the same way, we see that the two lines on the other side they also coincide. Okay, now we consider the pair of lines, AC and BC. These two lines intersect at C. These two lines intersect at G. So these two lines coincide. These two lines coincide. The two lines, they can intersect at only one point. This implies these two must be the same. the first pair of lines, AC and BC, they intersect at one point. Second pair of lines intersect at one point. However, these two lines coincide, these two lines coincide. Same pair of lines intersect at the same point. So C and G must overlap. Okay. So initially we shift EF to AB, then EG to AC, FG to BC. In this process, we also shift G to C. Now, this EFG is right on top of this. It's a superimposition. The two triangles are congruent.
Question.
Yeah, sure.
How come sometimes you use equal, but others sometimes you use congruent?
So it depends on what we are talking about. Are we talking about the geometric object, the triangle, or are we talking about the measurements? How large this angle is, how long the side is. If we are talking about the geometric object, this segment, we say they are congruent. But if we only care about the length, how long this is, they have the same length, then we say equal.
Oh, I see.
So sometimes we want, given the two angles B and F, of course they are different angles, but they have the same measurement. Even though I see the angle and angle, but actually this means is they have the same measurement. So when we say equal, we're talking about the measurements, length, size. When we say congruent, we're talking about the geometric object. This triangle and these two triangles, they're different, but they are congruent.
Oh, they're different, but they're congruent. I see.
Okay, so from there, we conclude. Okay, so that's a very good question. Maybe I say a little bit more about this. So in our class, to simplify the presentation, we use the convention. When we compare the measurements, we write equal. But if you go to different lectures, different professors, they may have different conventions. Some may separate the cases. Some will ask you to write whether the two angles are congruent, or the two edges are congruent. Okay, so it should be know what the teacher use in his setting. If he use a different setting, when you answer his questions, you should follow his setting. In our class, we use this setting, but in a different class, you may have different settings. Aaron, does it make sense?
Yeah. But
Okay,
so you're
if
saying
in
that
this
other
class, yes,
are you saying that other professors teach differently than you do?
it's possible. It's possible. Every professor is different.
I see.
It's very possible that you find a different professor has different conventions. Some may prefer a. This is also correct, but sometimes we say it's inconvenient. This gives us some convenience, but sometimes it's some ambiguity. Okay, so kind of a trade-off, whether we want to be precise or whether we want to be convenient. Some trade-off. Okay, should be aware of the situation. Okay, we will have 5 minutes break and we'll be back at 8:22. Let's have a break.
Okay.
Okay, so now we have learned several theorems. The last one, the Angle-Side-Angle Theorem. So if two triangles, they have a pair of sides with the same length and the neighboring angles are the same measures, the two triangles are congruent. We learned that side-side-side theorem. If two triangles have 3 pairs of edges with the same length, then they must be congruent. And we have the following property. When we define the isosceles triangles, we have 2 requirements: equal angle and equal side. This proposition tells us we only need to check the second one. If we can verify this, then this condition follows automatically. So this one follows from this one. Now we go the other direction. We say this, if we have this condition, equal angle also give us equal sides. Second proposition. If we have equal angles, that implies again, that means the two sides, they have the same length. It's not equal as a geometric object, but equal as numbers. Okay, let's see how can we justify this. A, B, C. Now we know the two angles have the same measures. We want to check these two sides. Amy, how do you prove this? Any idea? Where should we start? What theorem can we apply?
The S, I think.
Okay, nice. Let's try. So the first proof, color. Amy wants to apply SSS for the pair of triangles ABC vs ACB. Okay, let's check the 3 pair of edges. AB first, second, AC. Well, are they the same? This is what we wanted to check, right, Amy? We cannot use it yet. Okay, so not yet because are they? This is okay. So we haven't verified that they're the same yet. We only know that these two angles are the same measures. We wanted to check these two edges have same lengths. Okay, so this is not ready. What else could apply? How to justify, how to check these two triangles are congruent?
The ASA theorem, I guess.
Okay, the second attempt by ASA. Okay, what's the side? Which pair of sides would you pick?
AB equals AC, like Amy did.
But we don't know they're equal yet.
Oh,
We wanted to prove this. We cannot use it to prove it, right? Okay, so I'm going to pick BC for the first triangle. What's the corresponding edge for the second triangle?
DB.
CB, yes. These two edges, do they have the same length? Jessica, what do you see?
I don't know.
So one is BC, the other is CB. I claim they have the same length. Kira, what do you see?
Um,
Very simple, very simple. Do not
BC
overthink.
equals BC equals CB is basically just going in the other direction from between two points.
Okay.
So there would be the 2 points didn't move.
Okay, yes. Because it's the same segment. One go left, one go right. It's the same segment. That's why they have the same length. Okay, now the angles. If I pick angle B for the first triangle, Amy, what would the corresponding be for the second triangle?
See.
Angle C. Angle C. So it's the second vertex, second vertex. Aaron, I want to pick another pair of angles.
Let's see. Can A be an angle?
We want to apply the ASA, and we picked this side. Could we use angle A in the theorem?
No.
No. Okay. So what should we use?
Oh, wait, so there's two angles in this theorem, so angle C equals angle B, I guess.
Okay, okay. So I take angle C for the third vertex. It corresponds to the third vertex will be
Yes.
angle B. Again, so this one condition we applied twice when proving the theorem. We apply this SAS. So one condition we applied twice, then the ASA is applicable. We conclude the two triangles. From there, we see that the edges AB, the first, second, correspond to the first, second AC, same length. Okay, so this completes the proof. So previously we mentioned that different professors, different teachers, they have different conventions and different math books. You have this math books, the second book about geometry, they may have different conventions. If you change the books, you should double check what's the convention.
Wait, exactly what is a convention?
So, for example, one convention, do I use this for the same geometric object only, or do I use this for the same measures? Some book may say I use this for same geometric object. Some book may say I use this for the same measures.
Oh,
And in the future, you will go to a book, some book may use this, square root of -1, and some book only use I. There's no square root of -1.
so there's only I is imaginary number, right?
So because this one, if we use this, we may treat it as a square root, even though it's not a square root.
I see.
So different books have different treatments for this imaginary number. Some use this, some use this. And because the books, they're also changing. A book published 100 years ago, a book published 50 years ago, a book published maybe a few years ago, they're all different. Okay, so now we have the two propositions. The proposition 1 is this implication. Proposition 2, this implication. Now we combine them. We see that these two conditions are equivalent. One implies the other. Proposition 1 combined proposition 2. We have the following. Given a triangle ABC, equal sides is the same as equal angles. Okay, so that means equivalent. Okay. Okay, so this is about the equality. Next, we'll deal with inequality. A very useful theorem. Consider a triangle. If we know that one edge is longer than the other, another one, then we can compare the opposite angles. BC. BC. Oops, BC too short. And AC. This will be A, B, C. If one side is longer than the another one, then the opposite angle, this one opposite angle is A, and this one opposite angle is B. Okay, so it means longer sides facing bigger angles. Okay, so let's see how we prove this. Why? Why the angle A must be bigger than angle B? Any idea? Where should we start? How do we use this information? BC, CAC. This one is longer than this one. Okay, so to use this information, I will find a point on B and C such that the length equal to this. So because this is longer, we can find a middle point such that this two are the same length. Okay, let's use this. This BC bigger than AC. We can find D, a point on BC with AC. Okay, Amy, what do you think of this step? Can this be done? This is
Yeah.
longer. So we can find a segment so that they are the same. Okay, so now what we have is to emphasize this, make this red, this red. Oops, it automatically connected. It's too smart. Too smart. Okay, so now we have this. Okay, now let's consider the triangle CAD. what can we see about the two angles? Angle CAD, angle CDA. Kira, do they have the same measurements?
CAD, the turning point would be A, so that would be that one, and then
Uh-huh.
the other
This
one
is
would be
CAD,
on
this
the
is
D.
CDA.
So I don't know.
Think about it. We want to claim these two angles have the same measures. Why?
You could use the ASA again if you like.
Okay, so
Show
we
some
could,
inside between them.
but there's something is ready for us to use. So it's the proposition one. Let's go back to proposition one. It says that if the two sides have the same length, then the two angles same measures. We apply this to our newly constructed triangles. This triangle. We have equal sides. They have equal measures of the angles. Since okay, so by proposition one. Okay, now we will compare the angle A and angle B. So through this middle angle, I claim angle A is bigger than angle CAD, a turn at A. Aaron, can you tell me why this angle is bigger than this one?
Because the side is, oh, yeah, A to C is shorter than C to B, so therefore not A is bigger.
I'm comparing the angle A with angle CAD.
Oh,
Right? Angle A, CAD.
oh,
I claim this angle is bigger than this one.
um,
Okay, because it has, if we add the two angles together, we get an A, right?
yeah,
So this angle is bigger than a part of it. Because CAD is only part of angle A. We have another part over there.
oh,
Okay. Then we use the conclusion we just derived. This is the same as angle CDA. And now I claim this is bigger than angle B. This one is bigger than this one. See why? Amy, what do you think? Why this angle CDA is bigger than angle B?
Because the length CD is less than CB.
Oh, well, we haven't proved it yet. That's what we wanted to prove.
Okay.
We cannot use it just yet.
Uh,
Why? this angle is bigger than this one. Okay, I'm going back to the first theorem we learned this lecture. The exterior angle equal to the sum of two interior angles. Remember this?
Yeah.
Okay, I'm going to apply this. Let's check. Could we apply this theorem? If we look at this triangle ADB, this one is the exterior angle, right? It's the exterior angle, it will be the sum of the two interior angles. So
Oh.
again, the sum of the two angles is this one, so this is bigger than any one of them. Okay, so several propositions we apply in this very simple argument. Now, this one is bigger than this, and this is bigger than this. Therefore, A bigger than B. And see, to prove this, we used two propositions. One, so first we construct a construction. We construct a triangle with equal sides by the proposition of equal angles. Now, this angle is bigger than a part of it. This part equals this one, but this one is bigger than this part because it's the exterior angle. It's a summation of the two angles. So we have this chain of inequalities. We complete the proof. So longer sides, bigger angles. Yes, correct.
For the longer sides, bigger angles, that means longer sides have bigger angles, or does that mean like,
Facing bigger angles.
huh?
So this is a longer side than AC. The angle is bigger than this one. So longer side faces bigger angles. This is shorter side with smaller angles. Okay, next we go the other way. Other way, bigger angles, longer sides. If A bigger than B, then BC is longer than AC. Okay, so we go the other way. Let's see how we prove this.
Add a D.
Well, we could try that, but here is angle A is bigger than angle B. So it's supposed to, let's try. We can add a D. We wanted to add it over there. Okay, not there. If we add it here, because this angle is bigger than this angle. We can find a part of it such that these two angles are the same.
Oh, okay. So that means angle A.
It means AD and BD, they are the same,
All right.
the same length, but it's not very helpful. We want to compare AC and BC. So we will use something like this for the next theorem. Okay, so keep this in your mind. So now our proof is proof by contraposition. Okay, let's erase this. We will proof by contraposition. Okay, now test. What's the contraposition of this proposition?
Angle A is less than angle B, and then equivalent to BC is less than AC.
First, this is not
Wouldn't it be-
equivalent.
Wait, no,
Okay.
hold on, wait.
If BC is less than AC, then angle A is less than angle B.
Okay, it's more correct.
Yeah,
So-
that's what I meant. That's what I meant. That's fine.
Okay, so keep in mind how to construct contraposition. P implies Q, the negation of Q, negation of P. Okay. So we refresh our memory. Now let's write down the contraposition. So the negation of this is bigger, the negation will be less than or equal to. Could we conclude, now we want to prove the negation of P. Okay, so we have two cases. When it's equal and when it's strictly less. Okay, let me draw another picture with the two sides equal to each other. BCAC, BCAC. Hard. That's not easy to shift this. Okay, the first case, when they are equal, is the proposition we had before, equal sides, equal angles. Second one is what we just proved. Larger sides, bigger angles. Larger sides, bigger angles. Okay, so put these two together. We have proved the contraposition. Then this implies the initial theorem. Okay, so this is an example of prove by contraposition. We write down the contraposition of the statement. And we prove this by considering two separate cases. When it's equal, we get equal. Less, we get less. Put them together, we have the condition. Put them together, we have the conclusion. So therefore, this is correct. This also correct.
So it's basically a win-win.
Okay, okay. Okay. So now if we put them together, summary. Oh, long and bigger, I got them confused. Okay, in a triangle ABC, the longer sides always facing the bigger angles. Or in other words, shorter sides, smaller angles. It's the same thing.